Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. We've proved mathematically that measurement error in x shrinks the estimated coefficient. So now let's see exactly why that happens visually. So no algebra in this video, we're just going to build one picture and add up to it. I'll show you also a very quick demonstration of how it would look like in a software. But for now, for you to understand how exactly we get to that final conclusion, let's start by drawing a clean scatter plot. So let's assume this is our data. We've got X, we've got Y. Maybe I could actually do them just slightly more clustered together so that I can exaggerate when we have the measurement error. Okay, so this is the scatter plot and this is our upward sloping line, the fitted line. This is the true relationship between education and income. So let's thinking this education and this is income. Okay, so the OLS line fits very fine right now. We can also assume this beta 1 hat in here is 3. So that's like our true relation. Okay. Now, suppose education is measured with error, okay? Before I show you what happens, try to think which direction do you think the points move, okay? Up and down was when you had the error in Y. So this time, the points move left and right. So we are going to move several points horizontally on our diagram. So some will drift left, some will drift right. So let's say these might drift left, these might drift right, this one right, this one left, and so on. So ultimately, what we have done is that the values of Y have not changed. So if I were to have horizontal lines in here that show all of the values that need to be translated into a new graph, okay? So what I would have is that this value Y that I had in here should also exist in here, but this point right now has actually, let's say, moved to the right for me. So instead of it being here, now it's going to be right here as a new observation. And then I would have another line which would be, let's say, my Y value is right here. So as you can see, maybe this particular value moved more to the right. So now it would be, let's say, here, while the other values moved one here and one here. So if I kept doing and filling this up for the entire thing, this cloud would look maybe, let's say, more like here. Okay, and if I tried to fit a line in here, what I will see is that it's looking more like this. Okay, so this looks now more the relationship compared to the red line, it's definitely flatter. Okay, so what has happened in here is that the cloud has stretched sideways. It's wider along the x-axis, and the points that should be far from the mean of x have been pulled back towards it. So the signal, the true variation in education, is still there, but it's now buried inside a wider, noisier cloud. Okay, think about the spring analogy. Okay, so imagine that the true data points are like beads on a spring. Okay, measurement error, what it does is stretches the spring. Okay, spreading now the beads further apart along the x-axis. So the true relationship between the beads hasn't changed. It's just that their spacing now has changed. Why does the line flatten? The key insight, once again, was on the actual OLS formula. So we had beta 1 hat, which was the covariance of xy divided by the variance of x. And measurement error leaves this covariance unchanged okay? But what happens is that this numerator is inflated instead. And because this is inflated, it means like you have the same number over a bigger number, which means your beta 1 is going to shrink, okay? Because the ratio shrinks. And that means the slope flattens. This is why horizontal noise is so damaging, because it inflates the denominator without touching the numerator. So the fraction gets smaller and the slope gets pulled towards zero. But let's see an actual, a better visualization of what happens, especially when your lambda changes. So what you now see is a better scatter plot of education versus income. What we see here is like this assumed true slope of 3, and let's say the estimated slope was 3.4, and an attenuation factor of 1. So the data points will spread horizontally the moment that my measurement error in X starts increasing. So if I were to start increasing my measurement error in X, right, the more severe the measurement error becomes, the smaller the estimated slope is coming. So as you can see, the attenuation factor is becoming smaller, because remember, for us to get beta 1 hat, it means the true is multiplied by the attenuation factor. So if the true is not changing, attenuation factor needs to be becoming smaller and smaller for you to realize that now the slope is getting flatter and flatter. Okay, so the blue line tilts towards 0 while the green dashed true line is staying fixed. Okay, and attenuation again falls from 1 towards 0. So if I keep making these measurement error in X even more severe, as you will see, they keep stretching and stretching until finally, let's say measurement is 100 in here. What you see is like a line that it's like almost completely flat, okay? And you've got this attenuation factor of 0.09 in here. And look at the difference that happens between the estimated slope of beta 1 and the true slope. So from 3, we've actually been dropping and being pulled towards 0, and we see an estimated slope of 0.4. So ultimately, measurement error in X spreads the cloud horizontally, inflates the variation of X without adding any real relationship with Y, which is why the OLS draws a flatter line and the coefficient shrinks towards 0. Okay, in the next video, we'll put numbers in and compute the attenuation bias a bit more explicitly with a few exercises. So stay tuned, and I'll see you in the next video.